Welcome to this lecture series in group theory. We will continue our discussion on permutation groups. In this lecture, we will learn about the sign of a permutation and the alternating group. There is not much to recall, so let me just show you the problems. And now let's get started. So there is a certain polynomial that we will define. It's a multivariable polynomial. We have seen single variable polynomials before, but one can define polynomials which have multiple variables. For instance, one can talk about polynomials of this sort and so on. And I don't want to formally go into the definitions of those things. I think they are, even if you haven't seen them before, it should be clear what is meant. We will use multivariate polynomials only for this lecture and not beyond this. So let's just get started. So fix a positive integer and we consider, well, let me fix something greater than equal to 2. And consider this polynomial. So this features n different variables whose names are x1 up to xn. And the coefficients of this polynomial are supposed to be coming from whatever, let's say complex numbers. So that's just fixed something. Okay. So this polynomial is defined in this fashion. You pick every pair of positive integers with one less than the other and form this difference. This is in itself a polynomial, which we multiply across all such pairs. So perhaps an example will help. So if n equals 2, then this is nothing but that, because there is only one pair with this property, 1, 2, and that gives us this very nice linear looking polynomial. If n were equal to 3, then we have 3 such pairs, 1, 2, 1, 3, and 2, 3. So corresponding to 1, 2, we have that, 1, 3 gives us this, and 2, 3 gives us that. And that's what this polynomial is. So when we write this expression, of course, we mean that you can open these brackets by usual multiplication. Just kind of multiply them like we multiply things in high school algebra. In fact, not kind of, exactly like that. Like in high school algebra, we have seen things which have multiple variables, x, y, z, etc. And we just open these brackets with the same rules and it behaves exactly the same way. So there is really no need to formally define these objects. Anyway. And here is another example. So suppose we have a polynomial, we have a permutation in S3, which is given by that. Let's say it's a switch, basically. Yeah, so this is cycle representation of this guy. So we get a new polynomial. Out of this one and this permutation sigma, we can create a new polynomial. Basically, wherever we see x1, we write x sigma 1, and x sigma 1 is 2. X sigma 1 is x2 because sigma 1 is 2. Wherever we see x2, we write x sigma 2. X sigma 2 is x1 because sigma 2 is 1. And wherever we see x3, we will write x sigma 3. Sigma 3 equals 3 in this case. So let's just explicitly write this down. So x of sigma 1 is 2, x of sigma 2 is 1, then we have a 2, 3 remains fixed, 1, 3. So that's what this guy is. And we can make it look a little bit better. So a minus sign comes out to adjust for this, when we adjust the signs here, we get a minus sign coming out. Then let us shuffle. Let us put that guy here. So this is x1 minus x3. And let us take this guy on the right side. This is x2 minus x3. So we see that this is equal to minus p x1, x2, x3. So this new polynomial that we get is just minus of the original one. And this is not an accident. We will see a general phenomenon, which is really the heart of the lecture. All right, so this is some definition. And before I go forward, let me mention that this discussion about sign of a permutation is, one of the ways to get to the notion of sign. And there are other ways. To see an alternate way, one can look at Gallien's contemporary abstract algebra. In the 9th edition, chapter 5 discusses sign of a permutation and alternating group and all that. This discussion I learned from Hershstein, but yeah, this is just one way to do things. I find it very neat, and that is why I'm doing it. So let's make a side observation. It's a little bit of a detour. We have some positive integer, at least 2. We define x as the set of the first 10 integers and x tilde as something I want to define. So what is this? This is all subsets of size 2, or rather all subsets of X of size 2. Right, so if for instance n were equal to 3, then X tilde would be all of these things. So this is just a notation for the set of all the 2-element subsets of X. Okay. So suppose we have some permutation of X, then we naturally get a permutation of X tilde. How? Define sigma tilde from X tilde to X tilde as sigma tilde of a 2-element subset of X is simply this 2-element subset. So if this is a 2-element subset, then I is not equal to j, and since sigma is a permutation, it is in particular injective, we get sigma is not equal to sigma j, and therefore this is also a 2-element subset. So indeed, sigma tilde carries a 2-element subset to a 2-element subset. It's a legitimate map, and you can check that it is a bijection. So please check that sigma tilde is a bijection, and hence sigma tilde is indeed a permutation of X tilde. And here is another simple exercise. If sigma and tau are permutations of X, then the tilde that, the permutation that you get after multiplying sigma and tau, and multiplication here means composition, is same as the permutation of X tilde that you get by first getting the tildes and then operating. In other words, the map sigma tilde, the map phi from sim X to sim X tilde, which takes sigma to sigma tilde, is a group homomorphism. Right, so this is a simple exercise, and another simple comment is that if n were large enough, then, and large enough means maybe 3, just that should be sufficient, then this is in fact an injective homomorphism. So you can embed this group into that group, and that shouldn't be a surprise. This in some sense is a higher order version of that guy. So everything that you should that you can do here, you should also be able to do here, if that makes sense. Okay, so now we can define sign of a permutation. And that is via this lemma, that if n is some integer at least 2, and sigma is a permutation of the first n integers, then this polynomial that we get is either, so what does this equation mean? So this says that this polynomial, fix a sigma, then this polynomial is either equal to that or is equal to minus of that. So that's what this statement says. So this can either be equal to that or minus of that, no matter what sigma you pick. For instance, if you pick sigma as the identity map, then of course this is equal to that. No issues there. But if you pick sigma something else, then it can also feature a minus sign. We saw an example in the case of n equals to 3 in one of the previous slides. So let me just explain this via an example. Writing a formal proof of such a thing is not going to help. Let me explain this via an example. We saw an example for n equals 3. Now let us see an example for n equals 4. So suppose we have a permutation of the first 4 integers, n equals 4, and let's say it is given by that. Then, so this is equal to that by definition. We want to compute this and show that it is either plus or minus of that guy. So what is this beast? So here we will get x of sigma 1, which is 3. Then x of sigma 2, then that. All I'm doing is 1 maps to 3, so I write a 3, 2 maps to 1, so I write a 1, 1 maps to 3, so 3, 3 maps to 4, so 4, and that way. Then we get, x2 gives me 1. Okay, it's some computation, but the point is, we will just, first we notice that the terms that we get here are the same terms that we get here up to a sign. So for instance, we have x1 minus x2 here, we have x1 minus x2 here. x1 minus x3 is here, we have x3 minus x1. So there is a change of sign here. x1 minus x4 features as it is, x2 minus x3 features with a change of sign, this features with a change of sign, that features with the same sign. So basically these things just get shuffled and some extra signs appear. And the reason is very simple. Basically what is happening is sigma tilde that you get, which is as we saw a permutation of the two element subsets of the first four integers. That sigma tilde is in action here, except that it was also introducing new signs, because when you switch the order of two things, you get a sign. So let's put the things in place. So first we will write the x1 minus x2 term. Then we will write the x1 minus x3 term. x1 minus x3 terms appears in this fashion. Then we will write x1 minus x4 term, that appears as it is. Then x2 minus x3 term, that appears with a flip. Then x3 minus x4 term, that appears as it is. Then there is one more, which is x3 minus, no, which one remains? I don't know. So sorry, so I first should finish 2. So x2 minus x3 is done. x2 minus x4 comes with a switch. And now I should do x3 minus x4, which appears as such. So I take out one minus sign from this guy, one minus sign from that guy, and one minus sign from that guy. So a total of 3 minus signs means just one minus sign, and the rest is exactly as the original polynomial. So I hope this example made clear what's going on. And the sigma tilde is what's at play of the proof. You just have to apply sigma tildes to, kind of sigma tildes to these guys, but just take care of the signs. Every time you will get either a plus sign or a minus sign. If you multiply a bunch of plus and minuses, you either get a plus or minus. That's all. That's this proof. And I don't want to write it formally. So I hope this is clear. And now, final one more thing is that if we have, so we have this definition of the sign now. We can define it. Oops. So if sigma is a permutation of the first n integers, then sine sigma is an element of this set, which is defined as the unique number that you get here so that this equation becomes true. For any sigma, this is equal to either plus of that or minus of that. Whichever comes here, that is the sign of sigma. Okay? And if sigma and tau are in Sn, then sine sigma tau is sine sigma sine tau. Of course, there's a product here. This is also a group under product. So one can multiply things here. I mean, just like you multiply real numbers, or you can just think of it as a subset of real numbers. So this equation makes sense. So this is a fact, and this is just another way of saying that the map phi that we discussed earlier, which was going from sim. In our case, it's the first n integers. Let me write that in full. To sim the two element subsets of the first n integers, which takes sigma to sigma tilde, is a group homomorphism. Why am I writing this in blue? Let me change the color. Gray, let me put gray. So it just is a restatement in some sense of this fact, right? So I leave this for you to check. And what this shows is that, perhaps I mentioned that in the next slide. Yeah. So fix some n greater than equal to 2. Then the map, which takes a permutation to its sign, is a group homomorphism immediate from this statement. In fact, this is the same statement as this. And since it is a group homomorphism, we can consider the kernel of this guy. So the kernel of this guy is defined as the alternating group. Or you could say the alternating group, or the nth alternating group, is defined as the kernel of the sign map. Okay, so this is a group. And the elements of this group are called even permutations. The elements of Sn which are not even are called odd. So the elements here are called odd. And maybe one more final comment. This guy is a proper subgroup of Sn. In other words, what I'm trying to say is that this guy is surjective, meaning there always exist permutations which have negative sign. So by first isomorphism theorem, the index of An is necessarily 2. It's a proper subgroup and only 2 cosets. So why is it surjective? I will discuss this at length in the next lecture, but let me just tell you that any let's say you take sigma equals 1 comma 2. I mean 1 2. This, if this is the cycle representation of sigma, then sine sigma is negative, is -1. And this you should do as an exercise now, but the next lecture will get more detailed with these things. Okay, such things are called transpositions, which are very simple kind of permutations, and they're also building blocks of all permutations, interestingly. All right, so this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.